In this lecture, we will use z-scores to compare two scores in one distribution. We will also use z-scores to compare scores in one distribution with scores in a second distribution. Z-scores are often referred to as standard scores because they transpose raw scores into values which are meaningful in terms of how far the score is away from the mean into standard deviations. Look at the formula for calculating a z-score. You first find the score's deviation by taking the score and subtracting the mean. Then you divide by the standard deviation. If the deviation on the numerator is a negative value, it means the raw score was lower than the mean. Thus, when dividing by the standard deviation, which remember is always positive, the resulting z-score will be negative. If the raw score is the same value as the mean, then there is a deviation of 0. 0 divided by anything is always 0. Finally, if the raw score is greater than the mean score, you will have a positive deviation, and a positive deviation divided by a positive standard deviation will give you a positive. Think of z-scores as a number line where the value 0 corresponds to the mean. Z-scores to the right are positive and represent raw scores that were larger than the mean. Z-scores to the left are negative and represent raw scores that were smaller than the mean. One advantage of using z-scores is that you can easily compare two or more scores on the same measure or even on different measures. For example, there must have been around 200 people in my undergraduate physics class at CU Boulder. Our exams were not reported to us as percentages, only as raw scores with the distribution's mean and standard deviation. Without a bit of extra math, it was difficult to see just how well you performed compared to your peers. When I got my first exam's grade and it was a 255, I had no idea whether I should be happy or sad. Once I learned that the first exam had a mean of 230, I knew a little bit more about how I'd done. At least I scored above the class average. Then we found out the standard deviation was 22. Now I understood that I did pretty darn well because I was more than one standard deviation above the mean when compared to my peers. A second advantage to z-scores is that they do not require data to be normally distributed. The interpretation of how a score relates to the mean in terms of standard deviations is meaningful even if your distribution is skewed. Let's work our first example together. In this example, we're looking to find the z-score of a student who took a nationally administered reading test. A reading test was administered to third grade students nationwide. The national mean was 42.6 with a standard deviation of 2.85. If we're interested in one student's z-score, we can calculate it as long as we know what that student's score is in addition to the mean and the standard deviation overall. What I want to do is I want to start off each problem by making sure I gather the information from the word problem and list it according to the appropriate symbols. So the national mean, represented by x bar in this case, is 42.6. And the standard deviation, which is a capital italicized S, is 2.85. And then our score of interest, Julio's score, is just x, and it's represented with x equals 37. Now, before I start crunching and punching things into my calculator, I want to have a pretty good idea of what my answer is going to be. So to set that up, I'm going to use that number line we introduced. And I'll place 0 in the middle. And what we'll do is we'll line up z-scores with the actual scores on the exam, and we'll relate it to the standard deviations. The z-score of 0, remember, is the same thing as the mean, which for our particular test was 42.6. Right? Now, if I want to calculate, I'm going to set up 2 standard deviations to the left and 2 for the right, just for practice purposes. Oops, that last one wasn't really spaced right. Let's fix that. Standard deviations, no matter what, should always be equally spaced because they have the same distance between them and the previous point. So let's go to the right first, because adding I like. So I want to go +1 standard deviation to the right, which would be the same as a +1 z-score. And to calculate the value that goes here, the score on the test, I'm going to take 42.6, the mean, and add 1 standard deviation, 2.85. So doing the math here fairly quickly, and it's no shame to use a calculator, guys, because we all make mistakes. 45.45 would be the value for a z-score of 1, because it's 1 standard deviation above the mean. Tack on another 2.85 to get the second standard deviation, and you get 48.30. Now, give myself a little room here to work. If I need to go to the left, which actually I do in this problem, 42.6 subtract 2.85. Oh, I hate subtraction. I don't know why. It's not like it's that much harder. I just seem to make more mistakes. 39.75. Does that look right? Yep. Okay, so a z-score of -1, which is -1 standard deviation, would be 39.75. And let's get rid of another 2.85 out of that. 0, 9, carry 8, 6, 36.90 would be the score for a z-score of -2, or 2 standard deviations below the mean. Alright, now that I've got this set up, and I realize I did a little overkill here. I didn't really need to set up the whole thing, but I kind of want to practice it with you a few times. Alright, I want to look at just the score for Julio, 37. Alright, so I know that he's less than 42.6. So as I travel along here, and I get to the next one, 39.75. 37 is still less than that, so I'm going to keep going. And 36.90 is smaller, so I know 37 is going to be right before that. So this is an x of 37. So what I can do now is I can make a nice clean estimate of Julio's z-score. And I use those double squiggly equals to mean that it's an estimate. And I have x of 37 is approximately a z-score of -1, not quite -2, but really close, so I'm going to say -1.9-ish. Alright. Now that I have that estimate made, let's do the actual math. So my z-score formula was to take the deviation, which was the score minus the mean, and divide it by the standard deviation. So, substituting in my values. The score was 37, minus the mean, 42.6, and divided by the standard deviation. Now, cautionary note here. This is actually a pretty big deal if you're really calculator reliant. If you were to type in 37 minus 42.6 divided by 2.85 in your calculator, it will give you the wrong answer. Don't do that. And that's because your calculator understands the order of operations, and it knows that if you have in a string, so numbers after each other, if you have a choice between doing subtraction or division, it's going to do the division first, because that's the defined order of operations in mathematics. So to avoid the problem, simply do the top, hit enter, so take 37 minus 42.6, and that gives me a -5.6, and hit enter. Write that number down, and then divide in a second step. So -5.6 divided by 2.85 gives me a z of -1.9649 something something something. Okay, now this looks promising because it's agreeing with my estimate of -1.9-ish. Negative makes sense because I know it's below the mean. And now I just want to look at my rounding. Always keep 2 decimals when working with z-scores. That'll become obvious later why, but for now, let's just practice rounding. What I like to do is I like to kind of target the digits I get to keep. I get to keep all the way up to the second decimal, so I've underlined that. And then I want to look one number next door, just one, okay? Absolutely do not look at this 9. This 9 has nothing to do with how I round the 6, because it's 2 places away. Only look 1 place away. 1 place away is a 4. So because it's a 4, I'm going to leave that 6 alone. And that means my final answer is 1.96, negative 1.96. That agrees with my estimate. Always check that. So I feel very confident that this is the right answer. Therefore, Julio's test of a score of 37 has a z-score equivalent of negative 1.96. What does this mean? Well, it means that Julio really needs some help in reading. So you'll probably want to target Julio for some sort of reading intervention, maybe some extra time one-on-one with a para, something to make sure that he's receiving extra attention to bring that reading score up, because right now he's achieving well below nationally his peers. Example number 2. In this example, we're going to look at temperature data. Temperature of the room was taken every 5 minutes over a day and recorded. The mean temperature was 68.9 degrees Fahrenheit with a standard deviation of 1.2 degrees Fahrenheit. When Jan entered the room, the temperature was 66.8 degrees Fahrenheit. What was the z-score for this value, and how can you interpret this score? Just like in the last problem, let's start by gathering our information. I know the mean temperature, x bar, was 68.9 degrees Fahrenheit. And the standard deviation, calculated from all of those temperatures we recorded, was 1.2 degrees Fahrenheit. The score of interest in this case is the temperature Jan took, and that was 66.8 degrees Fahrenheit. All right, so we're going to make our estimate first. It's just a really good practice. I'm going to cut corners just a little bit, though, this time, because I can see that my z-score is going to be negative. And I know that because my x, my score, 66.8, is less than the x bar. Okay, so I'm just going to look at the negative side of my z-score. So if this is 0, and I've got negative 1, negative 2, negative 3, those are my z-scores. And remember, those will correspond to the mean, minus 1 standard deviation, minus 2 standard deviations, and minus 3 standard deviations. My mean value is 68.9. And to find the standard deviations to the left, I do a little bit of math. 68.9 subtract 1.2 gives me 67.7 for the first value. Subtract again, I get 66.5. And we'll go one more just for kicks and giggles. You actually don't need to, but you could theoretically keep going on, well, essentially forever. Not forever, though. 65.3. So 65.3. Now, let's get rid of that mess. So my actual score of interest, 66.8, treating this as a number line, 66.8 less than this, keep going, 66.5 is too far, so I'm going to guess somewhere in here-ish. So a value of x equals 66.8, weird point, gives me a z estimate of, let's see, it's not 0, it's more than negative 1, but not negative 2, so I'm going to say negative 1.8-ish. It's really not that important how close you are. The big deal is you want to make sure when you do get an answer out of your calculator that if it's not even close to this value, you recheck your math. Okay, so z-score formula is equal to the deviation, which is x minus x bar, over the standard deviation. So plug and chug. Z is equal to the score, 66.8, minus the mean, 68.9, divided by the standard deviation, 1.2. And don't forget, your calculator can play some mean nasty tricks on you because it's going to follow the order of operations. So make sure you do 66.8 minus 68.9 before you do the division. So if I do that, I get negative 2.1, and I'm going to divide that by 1.2, and I get a z-value of negative 1.75, and my calculator didn't give me any more numbers, so I don't have to worry about rounding. Now, this value of z equals negative 1.75 absolutely agrees with our estimate, so I feel very confident in this. It means that the temperature when Jan took it, quite frankly, was way below what it normally was. The temperature is going to vary over the 24 hours, depending on what the thermostat is set at, if it's programmed, if there's anybody in the room, if doors are being opened and closed. But bottom line is, she had every right to feel it was cold when she walked in the door because she was almost, 2 standard deviations below the mean temperature at that particular time. So to interpret it, was it cold? Yes, it was cold, and it wasn't just Jan, it was really cold. Alright, problem number 2, done. Alright, example number 3. In this example, what we want to do is we want to see what a patient's z-score is when compared to a whole bunch of other patients who takes a cognitive abilities test. The context of this might be that to take part in a particular drug trial, someone would need to score more than 1 or more than 2 standard deviations below the mean on this cognitive abilities test. So that's kind of why we would do something like this. Alright. Patient score is a 45. So I know that number, usually the first number we've been given is the mean, but you got to be careful. Make sure as you're reading the problem, you're matching the symbol with the context. The patient scores X, and that's 45. Then, missing parentheses there, it gives us a mean, X bar, of 52, and a standard deviation of 5. So once again, I see that I'm looking at an example where my mean is greater than my score. Oops, I'm going to write that a different way. My mean is greater than the score is the same thing as saying the score is less than the mean. So I expect my z to be negative. So I'm just going to set up my number line for the negative side again, because that's really all I care about. So if I have a 0, which is my mean score, and then minus 1, minus 2 standard deviations should be sufficient. So z-score of minus 1, z-score of minus 2. And I know that my mean is 52. Didn't give myself a lot of room there, but that's alright. 52 minus 5 is 47. Yay, easy math. 47 minus 5 is 42. And that's sufficient because my patient's score of 45 is going to be between 42 and 47. So again, I'm going to estimate my z-score somewhere around a negative 1 point, I think it's going to be on this side. So we're going to say negative 1.4-ish. Okay, and again, if you'd said negative 1.5 is your estimate, or even negative 1.6, not that big of a deal. Because what we're doing here is we're just making sure that our answer at the end of this whole thing makes sense. Okay, time for the math. Z equals x minus x bar over s. So z is equal to 45 minus 52 over 5. 45 minus 52 is a negative 7. So negative 7 divided by 5 gives me a z of negative 1. Great estimate. Negative 1.4. Because it's going to be 2/5, and 2/5 is 0.4. So I feel great about this score because it matches our estimate on the nose, and it makes sense because I know that my patient scored lower than the mean. Now, if the criteria for the particular drug test was that the patient had a z-score of negative 2 or more, then we would say that this patient is not eligible to take place in the trial. which could have been a good thing or a bad thing. But regardless, that's what the patient's Z-score is compared to all the other people that had taken that test. In this next example, let's look at two different Z-scores and how to compare them and why we would want to do that. In this particular example, we actually have two different students, and they're competing. They basically want to see who scored better on their standardized test. The twist of the matter, though, is that one student took the SAT math score, and the other student took the ACT math portion. So they want to know who did better based off of their raw scores and the nationally published means and standard deviations. Now, in this particular case, the SAT was taken by, let's see, I think it was Eleanor. So the SAT is Eleanor. We'll just call her L. And the exam itself had a mean of 516 and a standard deviation of 114. Gerald took the ACT, and his score was, oh, whoops, we forgot Eleanor's score. What did she score? She scored a 680. So I'm going to make that note here, x equals 680. All right, back to Gerald. Gerald scored, line them up, 27. And the data for those scores was a mean of 20.6 and a standard deviation of 5. Okay, so just a quick inspection of them shows that they're both above the means, if I compare them. 680 is greater than 516, and 27 is greater than 20.6. So right off the bat, I can't just say who did better, because they're both above the mean. And in fact, if I look at it even more, if I were to say above the mean, so let's keep things color-coded here. When we're dealing with two different tests, I think that's helpful. If the mean for the SAT was 516, then one standard deviation above that is going to be 730. Is that right? No, 630. 630. Always make sure it makes sense in your head. 630, and Eleanor was a little bit above that. She's not going to be to two standard deviations of the mean, which would be 744. Her score is really good, though. Her score is right at about 680, so I'm going to put it somewhere around in here. Okay, so Eleanor is going to have a Z-score of a positive 1 point, let's see, it's about halfway, 50 above that, yeah, about halfway-ish above the mean. All right, Gerald, same game. I'm only going to worry about the positive side of his score. There was a mean of 20.6. Oh, and thank goodness for nice, easy numbers to add, 25.6 and 30.6 to get my standard deviations of Z-score of +1 and +2. His score of a 27, somewhere around in here, and I'm going to estimate it's around a positive 1.4-ish, but they're so close that I don't feel comfortable just making a call based off of my estimates alone. So I want to actually do the math. So let's calculate Eleanor's Z-score. So I'll go Z sub L, and her value was 680 minus the mean 516 all over the standard deviation of 114. So Z for L is going to be 680 minus 516, which is 164. That is not a negative, that was just a bloop. Divided by 114. My calculator spits out the number 1.438. That is pretty close to my estimate, so I feel pretty good about that value. And now let's calculate Gerald's Z-score. Z of Gerald is going to be his score, 27, minus the mean, 20.6, all over the standard deviation of 5. Alright, so 27 minus 20.6 is a positive 6.4, 4 divided by 5 gives me 1.28, which again is pretty close to my estimate. I was a little high that time. That's okay. Now, from this comparison, I can see the winner. And the winner is L, because L scored 1.44 if we rounded it. Standard deviations above the mean on the SAT math. And Gerald, well, he did great. Only scored 1.28 standard deviations of the mean. So, assuming that both tests measure the same kind of ability, Eleanor has the higher score. In our last example, I want to work one straight out of your text. This is example or question 5.6 in Chapter 5 of Spatz 2011. In this example, what we're going to do is we're going to figure out which score is going to be dropped for one person's scores over a set of exams. Alright, so how many exams do we have? Let's see, first anthropology exam, blah, 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 second exam, blah, 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 third exam. Okay, so I'm going to have 3 exams. So I'm just going to make myself a little table so that I get all of my values put together without getting confused. So I've got exams 1, 2, and 3. And for each exam, Abelson's going to have a score to compare to the class mean and the class standard deviation. Okay, now let's gather the information out of the problem. So on the first exam, Abelson scored a 79, and the mean was 67, and a standard deviation of 4. On the second exam, he made it 125, class mean was 105, and the standard deviation was 15. And then on the third exam, the mean was 45. Oops, 45. Be careful that you put the data in the right place. Standard deviation of 3, and Abelson got a 51. Okay, now you can see why we'd need to do this, because since each of these exams had very different ranges and very different means and standard deviations, to figure out how well he did compared to his peers, we're really going to need to standardize these scores. So I'm going to make one more column here for his z-score. Okay. Now, in each case, he scored above the mean. 79 is greater than 67, 125 is greater than 105, and 51 is greater than 45. So I know in all 3 cases, his score is going to be positive. So I can't eliminate one of them right off the bat, which I could have done if he had maybe just tanked exam 2 and had a negative z-score. Alright, now, with a standard deviation of 4, it's pretty easy for me to kind of do this in my head, because I've got 67, and if I add 4, 67 plus 4, I get 71, add another 4, get 75, and add 4 one more time, and I get a 79. That means that if the mean was 67, and we added a standard deviation 3 times, that means his score of 79 was really exceptional. Could have been even the highest score in the class, because he would have had a z-score of plus 3 standard deviations above the mean. Alright, let's do the same thing. So in case you can't tell, I'm trying to kind of wean you off of just looking only at the equations and starting to kind of think about what these things mean and how to interpret them. Same game here for exam number 2. The mean was 105. If I tack on 1 standard deviation of 15, that takes me to 120. And another standard deviation takes me too far, to 135, because his score was a 125. Well, I can do this math in my head because I'm kind of a geek, and I realize that 15 is 3 times 5, so a score of 125 is actually a third of the way, so it's going to be 1.33, which is 1 standard deviation, here it is, plus another third above the mean. So this one is meh, whereas the first one was woohoo. Let's just check the third one to make sure. Alright, exam number 3, 45 was the mean. First standard deviation gives me a 48. Second standard deviation gives me his score of a 51. So since I added 2 standard deviations to the mean, That would give him a z-score, right, of +2. Also, very good. Not quite as exceptional as the first exam, but still pretty darn spiffy. So, even though Abelson outperformed his peers in all 3 exams, his scores, the lowest one, was on exam 2. So, which test should be dropped? The answer is exam 2, because the z-score of exam 2 was less than that of exam 3 and less than that of exam 1.